the degree of x squared is 2. And so for this to break down, you basically got two choices. It factors into a degree 2 and a degree 0, but that's cheating because any degree 0 factor is a unit, right? And so doesn't matter. Or it has to factor down into degree 1 pieces. And that's impossible because there is no degree 1 term here, right? You can get the same argument for x cubed, it's just a little bit more complicated. If you have a non-trivial factorization of x cubed, it has to factor into a degree 1 and a degree 2, right? And there is no degree 1 to make that work for you. So these are both irreducible, and notice so not only is this not a unique factorization domain, you don't even have unique lengths of factorization, right? Because the product of these 3 irreducibles here is the product of these 2 irreducibles here. Any questions on that? Here's a more subtle example. This is one of my favorite rings. How many of you have ever shown in your dark past that this is a UFD? Right? If you've ever had a number theory class, you probably use the norm. You might have even shown it in the Euclidean domain. How about this one? Anybody ever shown that one? This is another kind of classic number theory. Both of these are in fact not just UFDs, these are Euclidean domains. And you can use the norm. The norm is the Euclidean function, right? The norm of a plus bi is a squared plus b squared, and the norm of a plus b omega is a squared plus, well, I guess it's a squared minus a plus b squared, something like that.
Quick reminder, Euclidean means we can do the division algorithm.
That's right. That's essentially it. That's right. So you have this Euclidean norm function, and what happens is given any 2 elements, with one of them not 0, you can divide by the non-zero element, and either it divides in evenly, or you get a remainder that is strictly smaller by the measure of this norm. So let's look at this. What about this ring right here? This is what a really cool example. This is a kind of a weird ring. Notice that this is contained in C omega. Agree? Because you've got this thing in C omega. So so any ring that contains omega must contain the square root of -3. So this is a subring of this. Notice that this is a proper subring, because by the way that we've constructed this, there's no way you're going to get the 1/2 minus 1, or the minus 1/2 plus 1/2 radical -3, 1/2 radical -3, right? So notice that observe this, but because omega is -1 plus radical -3 over 2. So it's a quotient of two things that are both in this ring, right? Also, omega is a root of omega is a root of this polynomial. So there's no way that this can be a UFD. I think it's maybe a little bit easier to spot bad factorizations in the previous examples. Anybody see a bad factorization here? Okay. So I've got a follow-up there. Even I learned that in Tennessee. Here's the interesting one. I guess, so everybody, well, so I'm playing a little bit fast and loose. I guess what we really need to do is convince ourselves that these are irreducible, but you can use the norm argument as well, right? Same thing here. If you take the norm of 2, it's 4. If you take the norm of either of these, it's 4. And for this to break down further, there would have to be an element of norm 2 in the string, and it's easier for it to be done. Here's my follow-up question. Why is this not a bad factorization here?
It's not irreducible. Yes.
Nope, they're still irreducible. In fact, here's an interesting little ditty about this.
Or associated.
Everything right here, every irreducible here is actually prime in the bigger ring. As a matter of fact, that's another unusual stuff. What'd you say?
Or associates.
They're associates, right? Because notice. You know, to slip these two things in here, notice the product of these two is 1, so no harm, no foul, right? Because this thing is actually here. By the way, I notice I have a -1 here, but it doesn't matter, just add 1 to omega and you get this thing right here. Notice the product of these two is 1, right? And when I group this way, I get they're the same factorization in the bigger ring, but these units here that are in the bigger ring are not in the smaller one. And so when you strip those units out, these factorizations that are the same upstairs become different downstairs. So that's kind of a nice little sort of consequence of all this. Here is another theorem that I'm not going to prove now. Oh, well, you know what? I'm gonna restate it for them and I'm gonna prove part of it now. On the domain, then R is equal to both if and only if Rx Actually, that is kind of a good sign that this property is an important property because it's stable under polynomial function. So integrally closed, when you go to the polynomial, it's still integrally closed. That's a good sign that this is a worthwhile property. I'm gonna prove the easy direction. This. So this is sort of half proof. Later. I got that as a homework, and we're gonna actually develop some technology that will make this direction. How about this one? I'm gonna do this proof because, I think it illustrates something nice that we can do. Suppose Rx is in closed. I want to show that R is in closed. Okay. Let K be quotient field of R. So if K is the quotient field of R, what's the quotient field of Rx?
Yeah.
Rational functions in K. Actually, no, maybe I will. So anyway, let's continue with this. Suppose omega in K is equal over R. We want to show that it's already in R, right? So how do we do this? Notice that omega is in X, right? I mean, if it's in K, it's certainly in rational functions, and is integral over R. Rx. So what can we conclude?
It's algebraic.
Well, I mean, so. Okay, so omega is in Rx. And it's also in K. So I think that maybe we will try to tackle the direction here. I was thinking, you can do this with evaluation too, but I think we can. Let's try to do the other direction. Let's see if I don't get myself in trouble if I'm running something I thought of. Okay, so suppose. Now somehow I want to get that, Rx is integrally closed. So let's let, Okay, so let f of x and kx be integral over Rx. And I want to show that f of x is actually a polynomial. So this is any old rational function. Right? First of all. But f of x could be any old rational function. So I'm gonna make this whole claim. Why is that? We'll see what we've got. That is integral over Rx, which is certainly indicated, right? So f of x is integral over kx. Here's the rub, kx, x is u. And so if f of x is integral over kx, it has to already be in kx. Right? Because notice that of course the quotient field of Rx and kx are the same. They're both rational functions here. So f of x lives in this quotient field, it's integral over kx. Kx is a UFD. So so f of x and kx. Okay, we've totally got that right. And this makes our lives much easier because now we know that it's a polynomial with coefficients in field. It's not a quotient polynomial.
Multiply constant and AFX in RX, right?
Okay, so let's write what f of x is. With the a. Okay. We can assume we need to show each AI is in R. Right, that's our goal. Right. I'm gonna make an assumption. Uh, uh, suppose there's this AI thing in my arm. We can assume each AI, not R, going for a competition. Anybody know why? Well, so assume AJ is an R. Right? then AJXJ is in Rx and is integral. It's already in the ring, it's already in the polynomial itself, so it's already integral, right? So just subtract it off. This is in the interval closure of Rx as well. Right? Because, so if we like, we can assume that none of these coefficients are in R, if one of them is, because any of them that are, we'll just subtract them. So now we've got this polynomial here. For each AI is 0 or is not in R. In fact, let me put 6 possible, or is in K minus 1. So we can assume this polynomial, if you look at any of the coefficients, it's either at 0 or it's in K minus R, and we will assume that AN is not 0. Because otherwise I would pick a different program. Right. Now that I've reduced this, so this thing's an integral. Any ideas what the strategy might be? So we've got some equation of integrality, right? So there exists PIX and RX such that P0x plus P1x fx plus P2x fx squared plus Pn minus 1 x f of x Pn minus 1 is equal. How does that help? Well, so let's let P say M be leading coefficient. And of course, this is in R, because all these are polynomials. Let's just look at the leading coefficient. Notice the leading coefficient, this is this humongous polynomial, right? So the leading coefficient of this, actually, it's easiest for me to do this. Let me change this to M, right? Because there's no reason to suspect that these two should be the same, right? Notice that this gives the leading coefficient term of this is A sub n to the M, right? Everybody agree? the leading coefficient of this is the leading coefficient here. Well, actually, I guess what we need really is we just need to equate the m in power terms.
Just the other way around.
That turned it around. Yeah, and this is why. There we go. Thank you. This is a, for the end. And actually, let me see here. I guess what I do need here is. Actually, I need to operate off the other side because I've got, so the problem is that the degree of this may be very large, right? So, okay, I'll see. So how can I fix this? Problem is it may be all mixed in. I think we need to go for the constant term. So let's suppose first, it's not zero. So let me just fix this. I'm gonna make an assumption first, and then I'm gonna justify the assumption here. We first assume A zero is not zero. So A zero is in K, but not R. Okay. So let's do this again. F of X is info over Rx. So there exists Pix and Rx such that P0 X is P1 X of X plus P2 X of X squared plus okay, there we go. Now does anybody see what to do to get a contradiction here? Plug in, yeah, so do the constant term, because there's no mixing up there, or more succinctly, consider the homomorphism that goes from R to XR just by letting X be zero. Right, so this translates to P0 0 plus P1 0 F 0 P2 0 F of 0 squared plus P n minus 1 0 F of 0 n minus 1 so F of 0 n equals 0. And so what do we get here? Is this one?
A0 is integral for using R comparison.
The right. As R is integral closed. Notice that A0 is an element of the quotient field, of course, that is the root of a Monte polynomial, all whose coefficients are in R. A zero is an R, and this is a constant. Now, one might protest that what if a zero is equal to zero? That could be a problem for us. So suppose that where let's see, P zero PT. This is kind of the more general setup we have, right?
In the parentheses is in Rx and actually L is in Rx, right? know we need-
Right, X to the L is certainly an RX, but how do you
Yeah.
know the quotient is?
We need to prove that the thing into parentheses is.
Right, so
mode of our polynomial.
we have by assumption that this thing is integral, and we know that this thing is integral, right? But what about the quotient? What about, what's left over? Uh, uh, And I can think of an easy way to do this with some stuff that we haven't talked about yet. But I suspect that there's a way to kind of slip out of this. Let's see here. Yes, I know how. So here, notice X is a prime element, right? And so see if you can leverage that. X is actually a prime element of RT. In fact, if you have a polynomial ring, really have the full polynomial ring, then X is a prime element. See if you can write the equation down and leverage that to get the rest of this. That should work. There's also evaluation theory. So I'll let you kind of finish that off, because I didn't yammer on more than I wanted to about that. Okay, any questions? And, Oscar, I think this is gonna go into you made a comment about this last time, and I promise that we'll get to this. This is a very easy lemma, right? I mean, the proof is like very elementary. But it's kind of amazing that a lemma that I'm gonna give you here has a lot of good applications. But the proof seems so straightforward. Lemma 9-1-10. Let R be domains. And U a unit in T. So U is the unit of the larger ring here. Then U integral, or I'm sorry, then U inverse. U inverse is integral over R. If and only if U inverse is in R initially. Now remember what this is. R is a domain, T is some bigger domain that contains it, use an element of it. This is the smallest ring that contains both R and U. And the proof of this is exactly, I think, what you think it would be. You just kind of follow your nose on it. But like I said, it's amazingly useful. Let's suppose that U is integral, or I'm sorry, U inverse. Some x dn plus a n minus one, x n minus one plus a one x plus a zero and r x. And so let's just see what that means. This means that u minus n plus a n minus one, u minus n plus one, plus a one. No, I was right. That word put my parentheses. So that's what you get when you plug in u minus one there. And so what this means is u minus n is equal to a n minus one, u minus negative. Now multiply both sides by u to the n minus one power. So u there you go. U inverse is contained in RU. And this is reversed. Right? Because if you make this in the other direction, assumption that U inverse is in RU, then you get an equation that looks like that. And I'll just reverse everything that I did. Right? Any questions? Okay. Here is one more little limit that will be useful for us moving forward. This is another indication that the notion of integral closed is an important thing. Limit. Any intersection of integrally closed domains is integrally closed. So if you have a whole bunch of these integral domains that are integrally closed, any intersection of them is still there, even if they vary among their quotient. Let I in some index set, be our collection of integrally closed domains. we'll say quotient field of Ri is equal to Ki. And I'm not really gonna need that here, but I just wanna emphasize that they may have varying quotient fields. Let R and well, let me also, I didn't say it. So let's make sure that our intersection of these domains makes sense, right? I don't intersect rational numbers in Z2, right? So you can assume that all of these are in some kind of master quotient field, if you like. So let R be the intersection of all these domains, right? If omega is in K, quotient field of R, um, uh, right, and omega is integral over R. So suppose you have an integral element there in the quotient field. Then omega is integral over Ri for all I. Because R is contained in each of these Ri's, so if omega is the root of some monic polynomial coefficients in R, then it's certainly root of monic polynomial coefficients in any of these Ri's. Therefore, omega is in Ri for all I. So omega is in the intersection of Ri. And so there you go. Yes,
Do we have to say that the quotient field of R is contained over quotient fields of R?
well, it certainly is, right, because R is contained in it. So if you have R is contained in Ri, then the quotient field K is contained in whatever the Ki is. So I'm gonna leave you kind of with the teaser, right? Always leave them wanting more. How many of y'all have ever heard of evaluation domain? I know a couple of you have. So I'm gonna start with the notion of evaluation next time. So let me just kind of give this in form. An integral domain is called evaluation domain if for all A, B, in, we'll call it B, A times B will be divided by A. So this is what I'm gonna call evaluation. So here's the deal. And you can assume those elements are non-zero, although the statement as written is correct. So what does evaluation domain mean? It means if you pick two elements at random, one of them has to divide the other. I bet you all can think of a large class of evaluation domains.
Don't talk about order, right? It's on order.
What's that now?
You don't talk about A is less or equal than B, right?
That's right. You could put an order on this kind of thing, but so I always like value. I always like examples so that I'm not just making stuff up. Can anybody think of a evaluation domain? And I don't think, what's that?
Q or R.
Any field will be a evaluation domain, for example. Can anybody think of an example of evaluation domain that's not a field?
Yeah, that. So,
Right, and if you're not familiar with that. See, think about this example, in the formal power series ring over a field. And in fact, the field is very important here. Given any two power series, one of them divides the other. I remember thinking when I first saw the definition of this, it's like, these things have got to be really easy, right? I mean, they're fields and then a little bit of extra. But the little bit of extra turns out to be a lot extra. And in fact, this is connected very much to the notion of integrality. In fact, so here's my spoiler. If you have an integral domain and you want to consider its integral closure, it is the intersection of all valuation domains that contain it. Right? Which is not, I mean, how does this relate to integrality? It does, and we'll see that soon. Okay, any questions? All right, well, you won't see me, but you'll see Grant on, Friday, for the math club thing, and, yeah, if that, and I encourage you to be at the seminar today too. If I've messed up anybody's schedule, let me know, and we'll work it out. Other than that, I will see you on Friday, but not here maybe, and on Monday.